Hi guys, welcome back to AP Calculus. So in this one, it's a lot of just the notes, and the next one's is mostly the examples here, so bear with me, please. So in this section, we're going to go over what is an actual power series. We're going to talk about where the center is and the radius of convergence for a power series, and we're going to find the interval of convergence for a power series. All right, so first off, what is a power series? So we started making a Taylor polynomial or a Maclaurin polynomial. If we're centered at 0, I guess technically that is a Maclaurin polynomial instead of a Taylor polynomial for e to the x the other day. And we got through a whole bunch of terms. I think we got it out to like the 5th power term. So this was the 5th power polynomial for e to the x. All right, so e to the x is essentially that, but we noticed that it looked like there was a pattern here. Like we noticed that it looked like it was x to the n over n factorial. And somebody even brought it up in class and said, well, isn't that like the power series or something? Or is that the series for e to the x? It is, it is. So now we are talking about infinite series. So we go to infinity, an infinite number of terms. And it is just that x to the n over n factorial. And we get all these terms, including here's the general term, and it just keeps going forever. All right, but these terms at the end, most of the time, if we plug in an actual x value, since they have this n factorial on the bottom, which gets really big really fast, these terms at the end get really small. But still, that is the exact approximation, if that's a thing, exact approximation. But that is exactly what e to the x is equal to as a polynomial that goes on forever, an infinite polynomial. And these infinite polynomials are called power series. All right, and each power series is centered at a particular x value. All right. When it's centered at 0, it looks like this. It has some term with n's or maybe numbers or something in it, and then times x to the n. So we get no x, then x to the first, x to the second, x to the third, x to the fourth, and so on, x to the n, and it just keeps going. Or if we're centered at, so this is centered at x equals 0. Or if we're actually centered at some value, if we set this equal to 0, we get x equals c here is for the center, c for center. This would be the power series. All right, so we have some coefficient for each term, and then x to this x minus c just keeps going to one higher power. It's to the 0, then to the first, to the second, to the third, to the fourth, and so on. All right, so that's centered at c, or c is just some number. All right, so something about power series, where they are centered, they will always converge. So like if I plug in 0 here, all the terms are going to be 0 except for that first term, because x to the 0 is 0. All right, so we would just get the first term. And same way if we plug in c here, we're just going to get a sub 0, our first term. All right, so if we plug in those numbers, that gives us our center. So if we just have x, it always means it's centered at 0. If we have x minus something, whatever that something is, that is where it is centered. So quick recap here. What is the center to this power series? X to the n over n. Well, we just set what's here raised to the n equal to 0. There's our center. All right, with this one, oops, this was supposed to be an n. I don't know how that got to be a 2. But we set this part equal to 0. And we get x equals 4 is our center there. All right, so it'll definitely converge at x equals 0 and x equals 4. Now the question is, where else will it converge? What other x values can I plug in here and here that it will still converge for? Well, it turns out it's just very close to these values are the places to start, and then to slowly get farther and farther away from those values and see what happens. All right, and it's the same distance each side of 0 here for this guy. So like here's 0, here's our number line, and it'll go a certain direction or certain distance in each direction, and then it'll stop. All right, and we've got to figure out how far it goes. Well, that direction is our radius. All right, it's the radius of convergence. All right, it's the largest value r such that x minus c, and sometimes c is 0, the absolute value of it is less than r. Or in other words, negative r is less than x minus c is less than r, and this series converges for all x in there. All right, so we would just add c to each side, and that would tell us, what it's between, but we have to find this r somehow. All right, so to find the radius convergence, we have two ways we can go about doing it. Either we can use the geometric series. If it looks like a geometric series, the absolute value of r has to be less than or equal to 1. So we set what's raised to the n here, less than or equal to 1. And we might have to move some numbers over or something, but that'll get us our radius of convergence. The other way to do it is using the ratio test. So the ratio test tells us basically this right here. If we look at the n plus 1 term over the n term, what ends up happening is this cancels out completely and just leaves us with this one factor here on top. And then we've got this a to the n over a to the n plus 1 over a to the n. And this can get moved over here to the other side. We simplify it and we move it over. And what's over here, what ends up being left over here is our radius. So we'll do some examples here in a second. All right, once we get the radius, so we have the center, we hit the radius. So we'll have, say, some center, x equals some number. We'll go up r, we'll go down that same r, and we'll get to these two endpoints, say a and b. Then we need to check what happens at a and b. So does it converge or diverge at each endpoint? So if it converges, we include it. So like if a converges, we would say it's a bracket. If it diverges, we exclude it. So we'd use the parentheses for interval notation, or we could use like a is less than or equal to x is less than b. That would work too, something like that. I like interval notation, but again, you can do it whatever you want. These are the only possibilities you can get. So open interval on both ends, closed in the lower, open upper, closed for both, open on the lower, closed on the upper, negative infinity to positive infinity. It means it converges everywhere. Or it only converges for just the center value, c. That would mean the radius would 0. So this one, the radius would be infinity, and for this one, the radius would be 0. All right, so our examples here, and then I think we're done for this one. So find the interval of convergence for each one of these. All right, so this one looks geometric. In fact, if I wanted to, I could just take the 3 out completely. And then it's just x minus 2 to the n, and it's exactly a geometric series. And this will converge if the thing inside here, x minus 2, the absolute value of that is less than 1. All right, so that means the center here is at x equals 2. If we set that equal to 0, this will always be 0. It would definitely converge if we're plugging in 0 over and over and over again. All right, if we actually solve this little inequality, actually this right here is our radius. All right, if we solve this, let's see, we add 2 to everywhere, all 3 sides, we get 1 is less than x is less than 3. All right, now we could check our endpoints, but for the geometric, we don't even have to, because the geometric, the rule is strictly less than. If it equals 1, that's a problem. Like we know if we plug in 3 here, 3 minus 2 is 1. 1 to the n is just 1 every time. If we just keep summing up 1, that's going to diverge. If we plug in 1 at the bottom end, 1 minus 2 is negative 1. It's going to oscillate back and forth. So this is our interval right here. Or we could write it as from 1 to 3, but this is our interval of convergence. All right, so from 1 to 3, and you can write it either way you want. So either one of those is acceptable. All right, now let's take a look at this guy. All right, so we've got x to the n, but we've also got a 2 to the n down here. So we can do this as a ratio test if we want. But we can also finagle this around so that the bottom is exactly 2 to the n. So we could say it's 2 times 2 to the n, and the top is x to the n, and that 2 is on the bottom. So we can be like, this is 1/2 x over 2 to the n, like that. And now it's a geometric, right? This is our r right in here, or lowercase r, different from big R. All right, so that means this will converge whenever... So it converges whenever the absolute value of x over 2 is less than 1. And it is actually centered, so we treat this as a geometric. And its center is, well, we just have x, so that means x equals 0 is our center. Now we can solve this inequality. All right, we can say, okay, well, this is the same thing as x over 2 is less than 1 is greater than negative 1. And we can multiply all the sides by 2. So we get negative 2 is less than x is less than 2. And right there, again, since it was geometric, we don't have to test the endpoints. All right. If it was not geometric, we would have to test it. If we did ratio, we had to test the endpoints because at 1, it's inconclusive. But here, since it's strictly less than, we know that this is the answer. Or we can write it like this, from -2 to 2. So that means our radius here, so it was centered at 0, we go down 2 and up 2. So that means the radius here would be 2. And the radius here was 1. All right, and this is the interval of convergence. All right, so now what this also means, if I pick any number between these two, like if I pick 1.9 and I plug it in here for x, it's still going to converge. We'd have the sum of 1/2 1.9 over 2 to the n. This would be my r in here, and it's still less than 1, so it converges. All right, so this gives me a whole interval of everywhere that it'll converge, whatever x values we can plug in, and it will approximate it for me exactly for whatever function this might be equal to. All right, so we could plug in 1.9 and we could get an exact value. We could plug in 2 and get an exact value. Well, 2 wouldn't work, but we could plug in 0, we could plug in 1, we can plug in any number between -2 and 2, not including those two, and that would give us an exact value because this sum converges. All right, so that's it for now. We'll do a bunch more examples on the next one, especially ones that involve the ratio test where you have to check the endpoints.